Okay, so this lecture 26 is a lot like the lecture 25, where we're going to find the empirical formula, but then we're going to go one step further because we know the molecular weight, or approximately 74. So we're going to do out this problem, which is very similar to one that we just did. Let me just get it here as a guide. And we're going to see that if we use 100 grams, we end up with this. And we convert these to moles. Notice I'm moving faster. I am skipping, but at this stage, if you don't see how to get here, you want to go back to the earlier lectures. So we let's see here, 1.35. So I'll just say it quickly. We have 100 grams. Use these percentages to find the masses. Very simple because we're using 100 grams. And then we convert to moles. Now when we do that, we end up with, we can find the empirical formula. We divide by the smallest number and hopefully get whole numbers. If we don't, then we might have to multiply through by the same number. By a single number to make sure everything is an integer. Turns out everything's an integer here. Now the empirical weight, EW, is going to be 48 plus 10 plus 16. So 48 plus 10 plus 16 is 74. So in this case, we can consider it AMUs, or grams per mole. But they say that the molecular weight is approximately 74 AMU. So what that turns out, what that means is C4H10O is the empirical formula, but it's also the molecular formula. Same thing. And that often happens. We saw that with methane. Methane, once we had the molecular formula, tried to convert it to the empirical formula, found that it was the same. So that was a fairly easy one because it was the same. Let's try one. I'm sure this one will turn out to be a little different. Okay, again, so we have 19.2 grams of nitrogen. Then we have, let's see if we can't do it this way. Then 9.64 grams of hydrogen, 49.3 grams of carbon, and 21.9 grams of oxygen. Okay, so convert to moles. So the percentages we went directly to went from the percentages directly to the grams, and now we have to convert to moles. And you might, as I'm doing these out, you see that I tend to keep all of the units of measure, including moles of hydrogen when we're dealing with carbon. Make sure that I put in moles of carbon, grams of carbon here. And you might be tempted on the exam to leave those off, and certainly as long as if I were grading the exam, if I could follow that through, that'd be fine. But the reason you want to carry those units through, even though it does slow you down, is you can get things mixed up along the way. And if you know that you have the wrong answer at the end, you can't figure out what, it might be very tricky to figure out what happened if you haven't carried those units of measure through. So it does take a little extra effort. I'm going to put the units on here in a second since I'm talking about them, but I want to get the values down here. And so this is moles of nitrogen, moles of hydrogen, moles of carbon. And I know these are big problems. I'm going to keep double checking to make sure I'm on screen. And then I'm just going to do a real quick calculation here to make sure that everything makes sense. Okay, so we have nitrogen, it's 1.37, hydrogen is 9.64, carbon, is it carbon? Yeah, thought for a second it was chlorine. That would be a bummer, but it's carbon. divide through by the smallest number, and that should ensure, as long as we've done it correctly, that we get whole numbers or we get something that's easily converted to whole numbers. So we n 9.64 divided by 1.37 is 7, so H7. Carbon 4.1 divided by 3.71. This is 3. Oxygen is 1. Now, this is the empirical formula. And we don't know what this is made of. It's nitrogen, hydrogen, carbon, oxygen. It looks like some sort of organic compound. Sorry, I didn't get that. So the empirical weight is going to be 14 plus, I'm just going to do it really briefly, 36 and 16. And I'll add the significant figures in there. But 14 for the nitrogen, 7 for the hydrogen, 36 for the carbon, 16 for the oxygen. And you want to have the right significant figures when we're done. This is 73.0. And since if we're doing it for one molecule, then it's 73 AMU. Now the molecular weight is 146.19 AMU. So this is where the term, and let me double check, different books have different terms they use. I believe our book currently uses N for the fraction, but before I say anything further on it, yeah. So N is the molecular weight divided by the empirical weight. Now if that turns out to be 1, if this is 1, then that means the empirical formula is the same as the molecular formula. I should have done that on the last one, but it was 74 divided by 74. The molecular weight here is 146. The empirical weight is 73. And let me get the exact answer. So we have 146.19 divided by 73. And this comes out to be 2.0026. And that's going to round the 3 significant figures to 2. That is the ratio of molecular weight to empirical weight. The empirical weight, or the empirical formula, we know is not necessarily the molecular formula. It's most likely going to be smaller. So and there's always an integer number of empirical formulas in a molecular formula. We've just divided by 2 or 3 or 4 or whatever. So in this case, it looks like the molecular weight is twice as much as the empirical weight, which means that the molecular formula is going to be N2H14C6O2. If you found the molecular weight of this, you'd find that it was 146 AMU. And so we know that and that seems perfectly reasonable because we get something that's very close to a whole number here. If this had come out to be well, actually, even if it was not quite an integer, we could work with it. But normally you end up with something that's very close to an integer. Okay, now let's see what else we got here. Here we go. So 3, you can see these are familiar from other lectures. So this compound has a formula weight of 522 AMU. So we have 5.53 grams of sulfur and 24.47 grams of chlorine. If we're going to find the empirical formula, which we'll have to do first, we have to convert. So this is 35.5. Boom, boom, boom. So we have 5.53 divided by 32. This is 0.173 moles of sulfur. And this is 24.47 divided by 35.5. And this is 0.689 moles of chlorine. So sulfur. So you can see it's the same problems. In this case, it's the same exact problem, but just going a little bit further. But you'll have to carry out the problem as if you're finding the empirical formula, which you are, and then you check if it says it has the. Oh, wait a minute! That one's right. And that is correct. Did I change this? Okay, so we have 0.689. Oops. Okay, yeah, I was going to say, this should be SCl4. I kept coming up with SCl5. So, whoops. So this is the empirical formula. The empirical weight should be 32 plus 4 times 35.5. So 35.5 times 4 plus 32. This comes up to be 174 AMU, or grams per mole, either one. Now, we know the molecular the formula weight is 522 AMU. So N is going to be 522 divided by 174. So this, you can see that they are different, so we're going to have to multiply through the empirical formula by a number, and it turns out to be 3. So in this case, the empirical formula was SCl4. The molecular formula S3Cl12. Make sure that's a 3. Yep. There we go. And this one, this number I just made up. I had said earlier, if you remember this problem that, oh no, never mind, this is a different one. I thought this was a hydrogen peroxide, so no, this should be fine. I just noticed that number was a little different. So we figured this out. We have 1.91 grams of CO2 and 1.174 grams of water. And I'll just do this out quickly all the way through, because I could check a previous lecture. I have them lying around here, but I don't have it handy. And by the time I found it, it would take about the same amount of time. So just for practice, because you'll have to do this, so I might as well do it. And then 1 mole of hydrogen is 1 gram. And as usual, I mean, this should be, if this is 3 significant figures, that's taken from the periodic table, so this should be 3. So 1.913 divided by 44 times 12. You end up with 0.522 grams of carbon. 1.174 divided by 18 times 2. We get 0.130 grams of hydrogen. And 0.13 plus 0.522. And subtract it from the original mass of 1 gram, we have 0.348 grams of oxygen. And this is something we've done many times. So you should know that those I just found those masses, subtracted it from our original mass of 1 gram, and came up with this value. So this plus this should equal the original mass of 1 gram. Now we have to go that next step. We take this, and I'm just going to do it quickly. So this is convert them to moles. 0.13 grams of hydrogen is 0.13 grams or moles of hydrogen. 0.348 grams of oxygen, divide by 16 grams per mole. And we get 0.218 moles of oxygen. Now we have carbon, 0.0435, hydrogen, 0.130, oxygen, 0.0218. This is the smallest number. That generally is the case for organic compounds. It's very, if you get into organic chemistry, you'll see it's very tough to, when you go by moles, to have more oxygen than hydrogen. It can be done, but it's just doesn't come up too much. So this is C2, and then 0.1 divided by 0.02. So this is H6O, and this is, so the empirical weight, again, really briefly, 24 plus 6 plus 16. So this comes up to be 46 AMU. And the molecular weight is 92 AMU. So N is 92 AMU divided by 46. And that comes up to be 2. as far as significant figures, I kind of let those go. But we're after a whole number, and 92 divided by 46.0 is going to still give us 2, the integer 2. So this formula should be C4H12O2. We just multiply through the empirical formula by that number. And that is the deal.